So far in chapter 5, we've been talking about how you can use derivatives and limits to help you graph a function. And the next step is to talk about how you guys can use limits to find asymptotes. So let's start off to continue on from our last lesson. We just talked about L'Hopital's rule and infinite limits. And one of the things we mentioned is that what you're actually doing when you're doing the limit as you go to positive or negative infinity is you're describing the end behavior of the graph. You're talking about what happens way off to the right or way off to the left on the graph. So on each end, either way off to the right or way off to the left, three things can happen. You can have a graph that turns up. We see that a lot, like just the arrow pointing straight up. We have the arrow pointing down. We have a graph turning down like this, curving down with the arrow pointing straight down. Or the third thing that can happen is you can have a horizontal asymptote and the graph flattens out. There maybe it twists and turns in the middle, but eventually it kind of flattens out to almost a perfect horizontal line. Those are our three main things that we're going to focus on right now. There are a few other things, like when we do trig graphs later in this year, they do different things for their end behavior. But for the functions we're looking at right now, these are the three things that can happen. So let's say we're going back to last lesson. We're doing the limit as x approaches either positive or negative infinity. First of all, just to be super clear here, as x approaches positive infinity, that's telling you what happens way off to the right. And as x approaches negative infinity, that's way off to the left. So just think of it like the x-axis. Positive infinity means a huge positive number. Negative infinity means a huge negative number on the x-axis. Now, of those three things, draw a little sketch here. So let's say we're graphing some function f of x right here. And we'll say we're doing the limit as x approaches, let's do positive infinity of f of x. So what we're actually describing in this situation is what's happening to the graph way over here. You know, we're not talking about the graph itself in the middle. We're saying if you go far enough to the right, the end behavior, the right end of this graph, what is happening? So let's say I take my function and I do the limit as x approaches positive infinity. If the answer is positive infinity, then what that means is the graph is turning up at the end. Now, if the answer to that question is negative infinity, that means the graph is turning down. So if you do a limit to, I'm talking about positive infinity, negative infinity would be the same thing but on the left instead of the right. If you're doing a limit to one of the infinities and your answer is positive or negative infinity, that just means up arrow or down arrow. Now the third one we talked about, if you do this limit as x approaches positive infinity and you get an actual answer, a constant. So let's say I get the answer 2. Say my answer is 2. If my answer was 2, what I would do is this. I would count up 1, 2 on the y-axis. I would draw this dotted line to the right, and I would say, whatever my graph is doing in the middle, eventually it's going to flatten out at that dotted line. Now, it could come from the top and flatten out, or it could come from the bottom and flatten out, but whatever it's doing in the middle, let's say that the graph is coming from the bottom. Eventually, for this end behavior, it's going to just flatten out like that, right at the line at y equals 2. So that would be what a graph would look like if the limit as x approaches positive infinity of f of x equals just the number 2. So those are the three things that can happen. Yellow is positive infinity, just the up arrow. Green is negative infinity, the down arrow. And in light blue there is what would happen if you have a horizontal asymptote. If you do your limit and you get a number, a constant for your answer. So let's go ahead and try a couple examples out. We're going to describe the end behavior of this function here. Now, first of all, when I say describe the end behavior, I want you to realize I'm actually asking you two separate questions. I'm asking you what happens way off to the right and way off to the left. So let's separate them. Let's do the right end behavior first. That would be the limit as x approaches positive infinity of f of x. Now, we just did these limits, we talked about them, and we said one of the tricky parts is realizing this is conceptual. This is, let me copy down the function itself real quick. 2x cubed minus plus 3x squared plus 4. So what we're really saying here is I am taking this really big number and putting it here and here. And we talked about something called the principle of dominance. We said if you take this number infinity and you start putting exponents on it, it becomes so big that really the only one that matters is the highest power. These other ones just become insignificant. So if I take this really big positive number and I cube it, it's still really big. It's bigger even. Multiply it 2, it's even bigger. So basically what I'm getting here is positive infinity. If I plug in positive infinity, I'm getting positive infinity. Now what that means in words is that my end behavior, this graph, is going up to the right. Now let's do the same thing for the left end behavior with the negative infinity. So to see what happens to the left, I want to do the limit as x approaches negative infinity of f of x. And what that would be, let me copy the question again, 2x cubed minus 3x squared plus 4. So now I'm going to take a really big negative number and put it here and here. I'm going to use the same thing. It's basically called the principle of dominance. I'm going to say, okay, let's really just worry about this first term here. It's the only one that's going to be significant. If I take a really big negative number, all you have to do here is be careful with your positive negative signs. If that was an x to the 4th power, then my answer would be positive infinity here, because when I raise something to the 4th power, even if it starts as a negative number, it ends positive. However, this is an odd exponent, so my big negative number stays negative, and my answer here is negative infinity. And what that means is this graph is going down to the left. So what I know so far, if I were actually graphing this function, I don't really know a lot about it. You know, we could go back and do our first derivative test to find minimums and maximums. We could do our second derivative, find concavity. But as far as what we've learned just from this one step, I know that after all that twists and turns in the middle, in the end, it's going to be turning up over here on the right and down over here on the left. And this is what we're doing one piece at a time, is we're putting all this thing to graph together. And in fact, in the next lesson, we are going to put it all together. We're going to take functions and we're going to graph them using end behavior, first derivative, second derivative, etc., etc. All right, let's look at one more example. Same question, describe the end behavior. So let's do right and left again. So let's do, I'll do right first. And I'll do the limit as x approaches positive infinity of, and let me just copy the question again, 3x squared plus 7x plus 2 over x squared plus x minus 2. Now, if you treat the top and the bottom separately again, where really only that highest power of x matters, then basically what we're getting is infinity over infinity for this one. That 3x squared is going to positive infinity, the x squared in the denominator also going to positive infinity. So this is an indeterminate form. Let's use L'Hopital's rule and try again. So leave the infinity for now, take the derivative of the top by power rule. That would give me 6x plus 7. And on the bottom, it would give me 2x plus 1. And that's still going to infinity over infinity. So if I do my direct substitution, if I plug in this really big number, on top it's going to infinity, on bottom it's going to infinity. So let's do L'Hopital's again. Remember, you can chain L'Hopital's rule. Keep doing it until it works. So the derivative of the top is just 6. The derivative of the bottom is just 2. There actually are no more x's. So there's definitely no infinity in this question. My final answer is 6 divided by 2, which is 3. So what that tells me is that this has a horizontal asymptote to the right at x equals 3. Now, to finish the question, what we should do is the same thing on the left. We should do the limit as x approaches negative infinity. Now, one thing I want to explain to you guys right now, the functions that we're looking at right now are fairly simple compared to what we will eventually look at. And because of the nature of the function, if it has a horizontal asymptote, it's going to be the same on both sides. Like if you do the work for the left, basically what will happen is this. As you're going to negative infinity here, you still get infinity over infinity, so you do L'Hopital's rule. This one actually comes out negative infinity over negative infinity, but that doesn't matter. You still do L'Hopital's rule again, and you end up with the exact same work where you get 3. So you also have a horizontal asymptote to the left at x equals 3. And just remember, for now, if there's a horizontal asymptote, it's going to be the same on both sides. But in the future, we are going to look at some functions that can be different. You can have a horizontal asymptote on one side and maybe going to positive infinity on the other side. Like think about e to the x. You guys saw the graph of e to the x last year. That has a horizontal asymptote to the left, but it goes to positive infinity on the right. So once we get to more complex functions, we'll see stuff like that, but for right now, it'll be the same on both. All right, let's quickly review vertical asymptotes because this is not new. We learned this earlier the first time we did limits. So here's our quick review. A function has a vertical asymptote if the limit as x approaches a. So we're not doing x approaches infinity again. That's for horizontal asymptotes. If x approaches some number, some constant, from either side, that's why I have the plus or minus on the a. The plus or minus is for left or right-sided limits. If it approaches a from the right or the left, or both, and the answer is either positive or negative infinity, then you have a vertical asymptote there. And remember, this is not new. We already did this. So basically what you want to do for your function, test any points that are not in the domain or are endpoints of intervals that are not in the domain. So basically, like anything where the function is undefined, test that to see if it's an asymptote. That's really what we're saying here. And then as one last quick reminder, when you're doing limits, if you get a constant over 0, that's plus or minus infinity, and that's what tells you that there's a vertical asymptote. So let's wrap up today's lesson with one example of that. And in fact, I'm going to do the same, review on domain, because you have to do domain to figure out which points to test on this. For domain, you're looking for the numbers that x cannot be, what makes the function undefined. And then everything else is in the domain. So basically, here's a quick review. These are the two main things you're going to be looking for. Anywhere the denominator is 0, the function is undefined and you need to test to see if it's a vertical asymptote. Anywhere you get a square root of a negative, the function is undefined, and then you need to test the endpoint of that interval. There are more, but those are the two we're going to focus on for right now. So now let's wrap up notes with an example. So what I've done, I took the exact same example that we just did for horizontal asymptotes, and now we're going to find vertical asymptotes. And it starts with domain. So when I look at this function, remember we're looking for two things. I'm looking for a square root, which I don't see, and that's good. If you don't see it, just forget about it. Then you're looking for a denominator that might be 0, and that's what I do need to do. So I'm going to take that denominator, x squared plus x minus 2. I'm going to set it equal to 0, and I'm going to solve it. And I'm going to solve by factoring. That would be x plus 2 times x minus 1. And that would give me x equals negative 2 and 1. So those are the numbers that don't work in this function. If I plug in negative 2 or positive 1, I'll get a 0 in the denominator, and the function is undefined. That means those are the only 2 points that even might be vertical asymptotes. So what we need to do is test each one. So let's do each limit. I'm going to start with the limit as x approaches negative 2. So I'm going to start with this one right here. And I'm going to do it by direct substitution. I'm going to do 3 times negative 2 squared plus 7 times negative 2 plus 2 over negative 2 squared plus negative 2 minus 2. Now, the bottom should be 0, unless you made a mistake earlier, because that's why we're picking these numbers. We're picking these numbers because they make the bottom 0. So the idea here is, if I do the top and I get any number, any constant over 0, that tells me it's a vertical asymptote. But if I get 0 over 0, it's not. It's actually what we called a hole back in chapter 3, and it's not a vertical asymptote. So let's see what that top comes out to. We would have positive 4, we would have 12 minus 14 plus 2. This one comes out to a 0 over 0. So what that tells me is that negative 2 is not a vertical asymptote. That got a little messy there at the end, but you guys get the idea. Negative 2 is not a vertical asymptote. So the only other one that might be is the positive 1. Let's test that one. Let's do the limit as x approaches 1 of f of x. So I'm going to do direct substitution again. 3 times 1 squared plus 7 times 1 plus 2 over 1 squared plus 1 minus 2. We definitely do get 0 on the bottom. Again, you can check if you want to, but like I said, unless you made a mistake on the first part, it's going to be a 0. And this time on top, we get 3 plus 7 is 10 plus 2 is 12. See, that's the difference. On the first one, I got 0 over 0. That means it's a hole. It's not a vertical asymptote. If I get any other number, any constant other than 0 over 0, that's a vertical asymptote. And that's my final answer to the question. The final answer is there is a vertical asymptote at x equals 1. And I'm going to put only here just to make sure you remember that I did test both of those numbers. And x equals 1 is the only vertical asymptote. All right, so before you guys go, just to talk about homework for the next 2 lessons, what we're doing, I gave you some problems from the book tonight, and the directions in the book say to graph the function, but my directions say do asymptotes only. Because what we're going to do is, for the next lesson, for the next assignment, you guys are going to finish the same questions. You're going to do asymptotes today, and then on the next lesson, on part 2, you're going to go back, you're going to not redo the work, use the work you've already done and finish the graph, which we'll talk about in the next lesson. But if you combine our 2 examples from today, that's what you're doing. Because in our first, I took the same problem, and for the first example, I did horizontal asymptotes. And for the second one, I did vertical asymptotes. For each homework question tonight, you guys are going to do both.